Okay, so if everyone can see my screen, I'll begin. Hello, everyone. My name is Pradhan, as Tapan mentioned, and today I'll be talking about well and seismic data informed uncertainty quantification in basin and petroleum systems modeling. We all know that a significant challenge in building a reliable basin model is the large amount of uncertainty associated with the input parameters. For example, in building a basin model, we need to specify several input parameters, such as geometries of interpreted horizons. We need to specify lithology-specific parameters, for example, porosity depth trends, permeability model, the thermal model, and many of which are uncertain. And uncertainty can also come from our boundary conditions such as paleo, heat flow, and sediment compaction mechanisms. While there is a lot of uncertainty, the good news is that we also have several data sets that can help us reduce this uncertainty. For example, we have data at the well logs, for example, porosity logs, the temperature logs, or the mud weights, which are direct measurements of the properties of interest, and they can be, and we've been routinely using them for calibrating our basin models. Note that these well logs, they are available at discrete locations, so they cannot reduce the uncertainty at locations away from the wells, but that can be, in theory, done by seismic data, which is spatially continuous. But you might ask that since seismic data is not a hard measurement of the property of interest, how can it reduce the uncertainty? Well, what seismic data measures is the travel times of the waveforms of the reflections that our geologic horizons reflect, and then what we can try to ensure is that our geological model agrees with our seismic travel times or waveforms. Right. So in order to do that, we'll be using an integrated workflow in this talk, and I'm showing that in this slide over here. What we do is we begin with basin modeling, and basin modeling gives us our normal outputs of properties such as pore pressure, porosity, mineral volume fractions. Now, in order to impose the seismic constants on the basin modeling outputs, we need to relate it to the PUF velocity of the rocks. And we do that using rock physics modeling, which is this component over here. And then once we have PUF velocity, we can constrain to our seismic travel times and kinematics. So note that in this workflow, we are doing two kinds of calibration. First, we use our well data calibration in a traditional sense as we do in the basin modeling. And then we also impose the spatially continuous constraints from our seismic data using the seismic imaging part. So this workflow has been was developed by Deeprisco et al. In 2014. One thing that they did not consider is the uncertainty propagation of uncertainties that are there in this workflow, and that will be the topic of this talk. How do we propagate and quantify the uncertainties in this workflow? In order to do that, I will talk about we employ a Bayesian approach. I will try to explain it using a very simple example. Let's say we have one-dimensional variables. M is our model input parameter. This could be, for example, your porosity compaction coefficient, and D is your data, right? And then we have a simple forward model, that is the data is 2 times the model parameter. Now, in the field, we have observed some data, for example, at the well logs, and then it says that my data equals 5, right? Then we know the answer, right, in 2.5, because this is a simple model. But when there is a complex forward model, for example, a Bayesian simulator, how do you know the real answer for the model parameter, right? And that's where the Bayesian approach comes in. What we do is first we define a probability distribution. On the top plot, this is a probability density on the model parameter. And then we say that 0 value has the highest probability and the probability decreases as we go away. This comes from our prior geologic knowledge. Then what we do, the second step, we try to infer from the data. We explore the model parameter space, typically using Monte Carlo simulations. We analyze a bunch of different values, and then we see where we match our data. I will talk more about this workflow as we progress along the talk, but the key takeaway is that there are two main components for this. The first is the uncertainty model parameterization, and then the second is the inference from the data. So remember that we are trying to constrain to two kinds of data, well data and seismic data. Correspondingly, each data will have these two components, right? We are doing a sequential workflow. So for the well data, we will first parameterize the uncertainty in the Bayesian model, and then we'll calibrate or infer with the well data. For doing the Monte Carlo inference, we are using a specific technique called approximate Bayesian computation. I'll talk about that as we progress along. Now, once we've done that, the second part is the seismic data, where again we parameterize the uncertainty on the seismic velocity, and then finally we calibrate or infer with seismic data using approximate Bayesian computation. Now, once we've accomplished these two steps for each of our data sets, we can quantify our uncertainty on the desired properties. Okay, so I will show this workflow using an application from the northern Gulf of Mexico. The data set that we have was provided by Schlumberger, and we are located here, offshore Louisiana. There are these two blocks, Ship Shoal and South Timberlake. And our analysis will be limited only to a 2D section. And this is our 2D section. This is the seismic line. This is the 2D line that was shown from these two blocks. The first step that we did was do an interpretation of the key geologic horizons that were present in this section. We derived the well tops from lithological interpretations, and we also had some biostratigraphic data. As you can see, we have salt at the bottom of the model, and our analysis will be limited to only the above the salt. So we won't be looking anything below the salt. And above the salt, we go as far as the Miocene-Totonian horizon in our analysis. Now, corresponding, this is our present day structural model corresponding to our interpreted horizons. And you can see that we have 10 stratigraphic intervals. Thus, our model will have 10 lithologies in this model. Okay, so coming to our workflow, the first step is we parameterize the uncertainty in the Bayesian model. So remember, I had this list of all the input Bayesian modeling, like input parameters which can have uncertainty. But here we do a selection of few of them, and that is because we have some well calibration data. We have a single well in our location, and that well has calibration data for porosity, mud weight, and bottom hole temperature. Now, since this data informs on some particular properties, we will only considering uncertainty in these parameters. For example, we consider uncertainty in the porosity depth trends. Porosity depth trend will be specifying by the usual Athys law, and the Athys law will have two parameters that are uncertain, that is the depositional porosity and the Athys compaction coefficient. Now, since we have some pressure data and some porosity data, we'll also be considering the permeability model as uncertain. For this, we'll be considering these three factors, for example, the permeability anisotropy factor, the scaling factor, and the specific surface area as uncertain. And we also have some temperature data, and that's why we'll also consider the paleo heat flow as uncertain. Okay. So as I summarized before, we have some lithological parameters which are uncertain. So we have 10 lithologies, and each of them have 5 uncertain parameters, and these are coming from the porosity model and the permeability model. So we have 10 lithologies. That's why we have 50 uncertain lithological parameters. We also consider the basal heat flow. This should be heat. Heat flow is uncertain. And thus we have a total of 51 uncertain parameters. And we will be using truncated Gaussian distributions to model the prior uncertainty, the prior geologic uncertainty on these parameters. One thing to note is that we had a gamma ray, and then the gamma ray had only coverage for some of these lithologies, and we know the weak lay from the gamma ray. But the top and the bottom lithologies, the weak lay was unknown. And this so this corresponds to your prior information, right? And this will take that into account when we specify our prior distributions. And I'll show that how. So what I'm trying to do is I'm trying to specify the probability density on the Athys coefficient over here. And as I said, we'll be using truncated Gaussian distributions. I'll only show the mean and the standard deviation, and I won't show the upper and the lower limits. So when I say this notation over here denotes a Gaussian distribution with the mean of 0.5 and a standard deviation of 0.14. Now, when I said we take into account the prior knowledge, for example, you can see that for a weak lay of 0.45, we have this blue curve which assigns some uncertainty on the Athys coefficient. For sandier lithologies, we have this red curve. But then we also have some lithologies, for example, lithology 1, where the weak lay was unknown. And in that case, we specify a larger uncertainty, and that's the black curve. So that is how your prior knowledge factors in when you specify your probability distributions. And in a similar vein, we also specify the probability distributions on the other parameters that we had from the permeability model and the depositional porosity for a total of 51 parameters. Okay, so once we've done parameterized the uncertainty in the Bayesian model, as I said, the next step is to infer using our data, and in this case, the well data. Now, coming to how do we infer, remember that we had talked about approximate Bayesian computation, right? we have some model parameter space. Now, what approximate Bayesian computation does is that it tries to generate Monte Carlo samples from this space, right? We'll generate, let's say, n samples, M1 to Mn. Now, every time we generate our model samples, we'll also forward model the data. So in this case, it will be our Bayesian simulation. So we'll run a Bayesian simulation every time, and we'll try to see what is our data. And now we have some observed data, that is our calibration data at the wells. Now, for this 1D example, it's very easy to find an exact match, right? But when your dimensionality increases, for example, seismic data, so it won't be possible to find an exact match, and that's where approximate Bayesian computation comes in. We say that we'll accept samples which are closest to my observed data, and in this case, which is 5. So if some of my samples, I generate 10 samples, if some of them give value which is very close to 5, I will accept them as my accepted sample. Okay, so then the first step is to generate these Monte Carlo samples, and we generate them from our probability distributions that we define. Then for each of these, so we generated 3,000 models, and for each of these parameters, we run a Bayesian simulation. And what I'm showing is the outputs of the Bayesian simulations of some of them, 3 of them, and here I'm showing the porosity realizations. And you can see that the outputs can vary because your input parameters also changes as sampled from the probability distributions. Now, this is your pore pressure realizations that we have, corresponding pore pressure realizations. And we also have the realizations for the temperature and then the present day elite volume fraction in our model. Okay, so once we have generated the Monte Carlo samples, the next step is inferring the data. So we want to find which are close to the observed data. What I'm showing is we do that in a probabilistic sense in this talk. What I've defined is the likelihood. For example, the porosity data, we have some hard measurement, and that is denoted by red. Now we specify some probability of matching. So we say that if I exactly observe this value, then I have the highest probability. I will assign it the highest probability. But as I move away, then I will assign it lower probability. So this is to capture the uncertainty that is existent in the data itself. Similarly, for the temperature data, we have a Gaussian distribution for the likelihood model. We also have some mud weight data, and mud weight data are upper bounds. That's why so this red over here denotes the mud weight data, and then we assign a probability density that has the highest probability at the mud weight data, and has a 0 at the hydrostatic pressure. So that is our likelihood model for the mud weight data. And then once we've defined this, we can select from our 3,000 models which are the models that match the data the best. And that's what I'm showing in this slide. The 3,000 models at the well location have been shown in gray. In red is our calibration data that was obtained at the wells. And then in blue, I've shown the 30 models which have the highest likelihoods. In other words, which are the closest to our data. And you can see that where we have data, for example, in this section from 4,000 meters to 6,000 meters, we have very narrow uncertainty in this blue, denoted by these blue realizations. But where the data is missing, our methodology gives us higher uncertainty. Similarly for the other data sets. Okay, so what we've accomplished till now is we have parameterized the uncertainty for the Bayesian model, and we have done inference with well data. The next step is to go to the seismic domain. In order to go to the seismic domain, we need to parameterize the rock physics model for the seismic velocity. So the rock physics model gives us a quantitative model for the rock microstructure. I won't go into the details of rock physics modeling. There are several excellent books and references out there, but what I'll try to focus on is that we have some outputs. We take the outputs of the Bayesian model, and that goes as inputs into our rock physics model. For example, we take the outputs of pore pressure, porosity, and smectite light content from our model simulations, and that we use a Cayley-Shand model, and that gives us outputs of the rock elastic moduli, from which we can compute the P wave velocities. And these are our corresponding realizations of the P wave velocity. Now, the next step is to perform the inference with the seismic data. In order to perform the seismic data, remember I said that we had to match the seismic travel times, right? So in order to match the seismic travel times of the reflections, we will employ something called the residual move-out analysis. So the residual move-out analysis, it doesn't want to be too happy or too sad. It always wants to stay neutral. What I mean by that is that what we do is we take our geologic model and we propagate our seismic waves. Now, if the model has the right velocity, then we'll have a flat gather. And that is when we know that we are close to our data. Now, if the velocities are too fast or too slow and we propagate our waves, they won't match with our observed seismic reflection travel times. And then we'll have this frowning gathers and smiling gathers. So that is how we measure in a quantitative way how close we are to our seismic data. Okay, so and I will show that over here. What I'm showing over here in gray is the 1000 basin modeling realizations, the velocity model in this VP on the x-axis, and this is at a location away from the well. And then I'm showing in blue the 30 models which do the best for this residual move out analysis, which match the best. And you can see I'm showing a seismic depth image over here, obtained with the right velocities, and you can see we have good definition of the reflectors. But let's say if we have too slow or too fast velocities, we can see that the image degrades, right? And that is how we can see whether our velocity model is right or not. And for comparison, I've also plotted we had a velocity model from the tomographic inversion, and that is in black over here. And we can see that our model has done very good in capturing the uncertainty around the tomographic inversion. But also at some places, the inverted model is falling out of the geological bounds for this scenario. And that is one of the advantages for workflow, that it gives us a geologically consistent velocity space. Okay, so finally, what I'll show is the how we can generate multiple models which capture the uncertainty. Here I'm showing the velocity model from tomographic inversion and the corresponding seismic image on the bottom. This is our one of the basin model which matched our data very well. Basin model, velocity model, and then this is the corresponding seismic image, and this is another one. And you can see that if I flip between it, you can see the reflectors shifting around, but all of this match the data very well in terms of travel times. So this is also a possible basin model, and that's how you capture the uncertainty as constrained by seismic data. Okay, so we've done, and then the final step is to quantify the uncertainty of desired properties, right? So now we've generated a bunch of models which agree with the well data and the seismic data. Now the part comes where we define the uncertainty, right? And here I'm showing is how the well data reduces uncertainty on some of the key input parameters for the basin models. For example, the heat flow. We had assigned a prior distribution which had this large range of uncertainty, but after considering the well data to the temperature data, we see a huge reduction of the uncertainty. Similarly, for the Athis coefficient in lithology 7, here we had data and we see a reduction of uncertainty. A good thing is that our data gives us large uncertainty where we don't have data or methodology. So, for example, in lithology 4, we didn't have any well data, and we see that the prior and the posterior uncertainty are almost the same. So now what I will show is uncertainty reduction with well and seismic data for the pore pressures. And we are looking at a location which is away from the well location. And here in gray, I'm showing the prior realizations. In blue, I'm showing the realizations which are constrained by the mud weight, that is only the well data. And in red, which are constrained by mud weight and seismic data. And I will show this analysis at different depths. And this is what I'm showing over here. I'm showing at depth of 1500 meters, 3000 meters, 4500 and 6000 meters. And you can see that the gray again is the prior, blue is the well, and the red is the seismic data. And you can see that as we go deeper, something interesting happens. Your seismic data says that your lower pressures are not possible. So you don't have hydrostatic pressures anymore. Rather, it says that we have higher probability of seeing overpressured zones, right? So it possibly identifies the seismic data existence of overpressured zones. In contrast, the well data is not informative away from the well location, right? And it still says that hydrostatic pressures are still possible, but seismic data rules that out. And finally, we can also get the spatial uncertainty estimates for some of our properties. For example, velocity, we can estimate the mean velocity and then the 90% interval. Similarly for the pore pressure. Okay, so coming to the conclusions, we saw that spatially continuous constraints from seismic data is helpful in reducing uncertainty on several basin modeling parameters away from the well locations. We introduced a methodology of approximate Bayesian computation, and that was very efficient in handling high dimensional data such as seismic data, and it efficiently allows propagation of uncertainty through the workflow. And finally, our integrated workflow, it enables building a geological model space for seismic velocity. And why can this be important? Because your seismic velocity model is always used in getting time depth conversion of geologic horizons, right? And remember that our basin model takes as input the seismic interpretations. And these interpretations are normally done disjointedly, right? And they might not be geologically consistent. But by doing this, our workflow, we can come up with a velocity model which is geologically consistent. Now, the good thing is that once we've done this workflow, we have a range of uncertainty. We can now go back and build the Bayesian model again, and hopefully, this will give us more confidence on our predictions. And that is what the topic of the next talk will be. Josue will show some preliminary results of closing the loop and how we can capture the uncertainty with our geologic horizons. And I'll finish with that. To wrap up, acknowledgements, Schlumberger for the data set. I thank Mustafa, who was a good friend of mine, and he developed the MATLAB uncertainty quantification toolbox, and which made possible running these Monte Carlo simulations with Bayesian models. I also thank Huile and Professor Biondo Biondi for their help with the seismic imaging parts of this workflow. And thank you to our affiliates for sponsoring us and making sure that we keep doing this interesting research. And I would be happy to take any questions that you might have.
So you can type, this is Allegra, you can type a question in the chat, and you can also type the question in the tiny URL for later. But if anyone has a question now, go ahead and type it, and I will feed it to Anshuman.